Hello and welcome, ladies and gentlemen. In this video, we'll be continuing our discussion of how to implement simple linear regression in R. In this video specifically, we'll be talking about how we can do inference in R, both by hand and using built-in functions. So for my stuff to start, I'm going to be doing the marketing and profit data sets, and then I'll have it in terms of X, Y, and I'll keep X bar just to make my hand calculations easier. I'll also start with the simple linear regression model so I don't have to recalculate a lot. Specifically, what I'm going to do with the simple linear regression model is I'm going to pull off the betas so I don't have to recalculate them here. Of course, we can do the recalculation doing the by hand stuff that we saw in the previous video, but I'm going to save myself a little bit of time by not worrying about it. So to pull just the coefficients, we use the coef, coefficient command. And then what I'm going to do with this is put square brackets after it. And for square brackets, it says, I want to pull just a piece of this. So I give it numbers. This is just a list of values in a vector. So I just give it the number of the piece that I want to pull. So for instance, if I give it the number 1, it'll pull the first number. And if I give it the number 2, it'll pull the second number. Well, the first number is the intercept, and that's the one I want to save as B0 for my upcoming calculations. I want to have B1 saved too, and that's going to be the second number, and I can just double check that B0 and B1 are matching my SLR model output. But remember, for inference on B0 and B1, I'll need these numbers later, so I'll just go on and pull those in this way. All right, well, once we're here, we can go on and begin our calculation for the sum of squares error / the mean squares error. So one of the first things I should do is kind of just look. These are the X values from my sample stored in the X variable. So again, I got a sample, I got X and Y values for marketing in X and profit in Y. I just got a whole bunch of data values. X stores all of my X values. What I'm going to do is I'm going to build my Y hat. And remember, that's a precursor to calculating some of these other things, because Y hat is my predicted values for each of the X values. So essentially what I'm going to do is do B0 plus B1 times X, which is my predicted X value. And in this case, which is my observed X values. And in this case, I get my predicted Y values for each of the X's. Now I'm going to save this as Y hat so that I can use this in a future equation where I compare Y hat versus the observed Y's. So that just looks like Y minus Y hat. And this is the distance between the observed value and my predicted value for that observation. So Y being the observed value, the dot, and Y hat being the line. E is going to be my notation for Y minus Y hat. That is residuals. And I see I had a typo here. That should have been Y hat. And my E are all of my error terms. That's the size of the distance between my predicted guess, the line, and the observed dot. And you know, actually here I have a little space to do just a kind of visual representation of what's going on. And graphing is not a huge part of this course. In fact, there's another course that you can check out that's involved almost solely with data visualization. So I encourage you to check out that course if you're interested. Graphs are a hugely useful thing. So don't hear me downplay them. But in our course, they're just not a main focus. We focus more on the analytic techniques. With this said, learning to graph can help you really understand what's going on. And maybe this example will help to illustrate how this can happen. All I'm going to do is put some points on a graph, nothing that you can't do after this video, and just put them on with a couple of colors. But I think these are going to help tell a story and might help to illuminate a little bit if you're a bit confused about what this observed and expected or the predicted Y hats, what these things are talking about. So let's start our story with a plot of X and Y. So this is the basic graph of my X and Y data. That's where we're going to start out. Now what I want to do is I want to add on the line. So I'm going to do AB line. A is the intercept and B is the slope. And I'll just type out B0 and B1 so that we can see this intercept and slope. And you'll note if I do a semicolon, that says to run these separately. So add the line and then print out what's in B0 and then print out what's in B1. And so you can see this is a line with the slope of 6.12. That's for every x value. It goes up when x goes up by 1, this goes up by 0.6. So as x goes up by 1, this goes up by about a half. And then the intercept where it meets the y-axis when x is 0 is negative 2.76. We actually discussed, and maybe this is worth mentioning at this stage, how the x value of 0 wasn't really in this data set, and maybe you can see that now. It looks like maybe in this graph the y-intercept should be, I don't know, like just under 1, but this graph isn't representing the y-intercept. This graph is representing just the plot of data and giving us a little bit of boundary around the observed data. For the y-intercept, we'd have to go and tell the plot, no, we want this to go all the way down to 0. Actually, I'm kind of curious. Maybe this will help. Let's do xlim is the command. You don't have to do this unless you want to. I'll do it from 0 to 10. This is the x limit. And you can actually see this is how far my data points are from 0. This is my y-axis line right here, x equals 0. And these data points are way far away from that. So when we make conclusions about the y-axis and the y-intercept, and you hear me say our data aren't really close to that, so we're extrapolating a lot. This is why I say that. We're essentially using the pattern here to predict that we're going to have a big loss down here based on what we're seeing and extrapolating that all the way down to the bottom. So maybe not a good place to make a decision. But anyway, that's not the focus of right now. The focus of right now, we've got our data and we've got our lines. All right, so here's what I'm going to do. What I'm going to do is put the y-hats on here. So I'm going to use the points command. This just adds data points. So I'm going to do x as my x value and y hat as the y value. So what I want you to see is what are all these y hats that we made. These are all the y hats. I want you to see what are these graphically. So these are associated with the respective x values. Remember, we plugged in the x's to get them. I'm going to color these red. So I use col equals red to color these red. And I'm going to do PCH equals 16. Essentially, what this means is R's default is to do open dots. PCH 16 says fill in the dot. So it's going to be filled in. All right, so let's put these points. I'm going to do Control Enter, put these points on the graph. And that's what our y hats look like. They are all points on the line because we're using the line to predict. In this case, this is the point on the line associated with that particular observed value. I used all of my observed x values, so the observed x value from this point, to say what would I have predicted that dot to be. And I would have predicted it to be this value, the red dot on the line here. What would I have predicted that value to be? Well, I plug in that value's x value right here into my equation for the line, and I get that y value that's on the line. That's my y hat. And I do that for each of these values. So all of these red dots represent the y hats, and these are the predicted height of each of these open dots when I look at them. So if I want to do points x comma y, I'll do col equals blue. So what are my y's here? And PCH, I'll fill in the dots, 16. Well, my y values associated with x are each of these blue dots. And so each of these blue dots are the observed y's. And so when I say y minus y hat, think the blue dots minus the red dots, and that difference is the distance between them. And we call that E for error, or our observed error, the residuals. All right, well, that's enough playing with graphics. I hope that was kind of helpful. But yeah, it's kind of nice sometimes to be able to plot some things to just look at and see, okay, well, what is that? What are we actually talking about here? So let's jump back to it. So for our error, we need the squared errors. Remember, we have the sum of squared error. E represents residual, the observed errors. So we're going to take each of those, we're going to square them, and then we're going to add them all up, sum E squared. And this is going to be the sum of squared error. So I'm just going to say this as SSE, sum of the squared error. Now for my degrees of freedom, and remember I need the sum of the squared error and the degrees of freedom for error. For degrees of freedom error, I needed the sample size which was just however many observations are in my data set. X and Y both have the same number of observations. Remember, these are data pairs. So I can just ask how long X is or how long Y is, how many numbers are in there. Either of those would give me my sample size just fine. P for simple linear regression, this is how many independent variables do I have. In simple linear regression, the answer is always 1. In multiple linear regression, you might have to think about it, but just think, how many variables do I have, independent variables do I have? And then my equation for the degrees of freedom for error is n minus p minus 1, or in this case, that's going to be 5. For my mean squared error, I simply take the sum of squared error over the degrees of freedom error, and that is my mean squared error term. I'll go on and save that for using later. Remember, we also called this s squared. And incidentally, for s, that means I need to take the square root of s squared, or the square root of this MSE. So s is 1.2547. And remember, this is the real thing we're after, because this serves as a foundational component when we're doing the standard errors for each of the p's. So this is the foundational component in the standard error terms. Real quick, let me give you a couple of built-in functions for like doing this by hand. The first one is when we're looking at the simple linear regression model, we can do sigma SLR mod, and this, believe it or not, is S. So I can quickly, from the model, pull this S value without doing all this work here, just by doing sigma of my simple linear regression model. So if I want to build anything by hand, but I already have the raw data, and I don't know why you'd want to build it by hand if you had the raw data, but you know what? Crazier things have happened. You can do that. If I want the mean squared error, you can just take that S squared, and this is the MSE, or S squared, of course. And then it's worth mentioning you can do an ANOVA of the SLR mod. Wrap that in an ANOVA statement, and you can quickly see this is the mean squared error. So you can pull the MSE, this MSE term here. This is the same as in the ANOVA table. So if you prefer to get the sum of squared error, the SSE, from the ANOVA table, or the MSE from the ANOVA table, just do ANOVA, put your model in it, and you can get those components pretty straightforward and easily. All right, so we're not done with our inference. That's just some built-in ways to get some of the components that we need as we're building up to our inference stuff. But now it's time to do tests and CI for our betas. And remember, beta is the population slope and intercept, beta 0, beta 1. And let's show these by hand, and then we'll do the built-in stuff. Cool. All right. So we are going to start with our B0. Remember, this is our point estimate. Then I'm going to have S sub B0. This is my standard error. And my equation for this was S, which I found earlier right here, times the square root of 1 over n plus, and I'm just reading my equation over here, x bar, the mean of x, squared, divided by the sum of x minus x bar quantity squared. And you'll note, be careful, I'm squaring and then taking the sum after I've squared, and then I'm wrapping up the square root. So that's my values there. I'm going to save all of that as my S sub B0, and this is my standard error for the intercept. And I have my critical value, and I'll just do the same one for a two-tailed and one and two-tailed test. Take my alpha level, in this case 0.05. I'll do that over 2. Degrees of freedom is the degrees of freedom for the error. And again, I tend to do the lower dot tail equals false. Remember, you need the plus and minus. And now that we're back with the t-distribution, this is the plus and minus of the same number, but I tend to do the positive version, and then when I put it in like a confidence interval equation, I'll just do plus minus the positive version, and that'll get both sides. All right, so now we can build our test statistic pretty easily. The test statistic is the point estimate, B0, divided by the standard error, S sub B0. And that's my test statistic. And if I wanted to put P0 on top, I might do, minus P0. In this case, it's 0, or PE sub 0. In this case, it's 0, but it'd be whatever it is, in that case. And yeah, this is my test statistic. So TS equals this. Why do I save TS? I always save it because we'll need it to calculate the p-value later. So if you wonder why I tend to save that as a variable but not everything else in the results, it's because this one I use when we calculate the p-value. We already know the critical value. We actually already found it. Again, we use the positive one, but for our two-tailed test, this is positive and negative. If you're doing a one-tailed test, you would have to recalculate the critical value. So you'd use a different critical value for the one-tailed test than you would for the confidence interval. So you would do the two-tailed for the confidence interval, and then for the hypothesis test, you would recalculate using a one-tailed critical value if you wanted. So in any case, our test statistic is not bigger than the critical value in the positive or negative direction. So we don't have enough evidence to reject the null hypothesis. All right, for the p-value, well, this is a two-tailed test, so I don't know which direction I'm going, so I'm going to have to run this twice. Give it my test statistic. Degrees of freedom is the degrees of freedom error. I'll do it lower.tail equals true. This is looking in the lower direction. Oh, and I used the wrong command. I used QT, but for a p-value, you need to use PT. So I'll look in the lower tail direction, true and false. So this is the smaller one. Remember, I take the smaller one and multiply by 2. This is my p-value. P-value. There we go. Again, because it's a two-tailed test, smaller one multiplied by 2. All right, p is greater than alpha. That's not significant. What does that mean? There's not enough evidence to change my mind. I went in believing it was 0, and I didn't see enough evidence to change my mind. So I'm sticking with the belief that it's 0. Cool deal. Confidence interval. Remember this point estimate times plus or minus critical value times standard error. Point estimate is B0 plus critical value times standard error. And again, if you're wondering what each of these numbers are, you can just highlight it and hit Control Enter, and you can see each one of these numbers on their own. Of course, you can copy and paste numbers if you want to take the calculator approach. But, we're getting kind of late in the class, so I think you've kind of already decided and gotten the hang of what you're doing. I hope this has been helpful for you, seeing how you can kind of use variables. I think they make life a little bit easier, especially when copying and pasting stuff. But always up to you. And just like from the equation standpoint, I find them easier. But again, always up to you. Cool. And that's my confidence interval, 3.875 to negative 9.414. All right. Well, let's keep going. So let's move on to tests of the slope. I guess I don't want to make that a section. We'll just do a lot of hashtags. So for my test of the slope, again, I need my point estimate, standard error, and critical value, B1, that I already calculated. This is my point estimate. So I'll be using that throughout. The standard error of B1, again, uses that S that we calculated earlier up here. This S value right there, calculated earlier in this video, divided by the square root of this sum of x minus x bar quantity squared. Again, that's a popular thing. Oop, I need to be able to type here. X bar, so I close out. Oh, see, I'm messing all this up. I need to take the difference, then I need to square it, then I need to sum it. Perfect, that's what I want. I'll just highlight and run that, see what that number is, just for my own curiosity. And then the critical value is the same one as I calculated above. I'm not going to worry about changing that. Again, we have the same degrees of freedom as the degrees of freedom for the error, and I'm using the same alpha level, so nothing's really changed here for the critical value. Test statistic is super boring. B1, the point estimate over the standard error. S sub B1, boom, super boring. Test statistic is this guy. Critical value, again, we already found. So comparing our test statistic to critical value, got the plus and minus version because it's a two-tailed test and the test statistics in between. So nothing interesting going on here. Came in assuming marketing and profit weren't related and didn't change my mind. Looks like they're not. Or there's not enough evidence to determine they are. It does not look like they're not. That's not the conclusion. It's just that there's not enough evidence to determine that they are. All right, lower dot tail equals true. And again, I run this both ways, so I'll just copy and paste this. I won't even look at it before I run it. True and false. So this second one is the bigger one in this case. So I take that second one times 2. This is my p-value in this case. Again, I just look for the one that gives me the smaller number and multiply that one by 2. And that gives me my p-value. All right, well, let's do the confidence interval here. And then we're kind of done with the by hand stuff. I mean, I hope this is feeling somewhat anticlimactic. Point estimate, plus or minus critical value times standard error of B1. And point estimate minus critical value times standard error of B1. The point here, I would say, or one of the points that I hope you get away from this is, you know, we've actually already done a lot of work in this class. If you've been following along with the course, you've been using R essentially all semester for doing various calculations. Again, in this course, we've kind of phrased things in terms of this point estimate, critical value, and standard error. And hopefully that makes, as we start to approach these things at the end, in terms of the test statistic, in terms of the confidence interval, in terms of how we structure our problems, these actually become quite a bit simpler to structure than if we had to memorize a new equation for each thing. Really, we just have one equation, point estimate plus or minus the critical value times the standard error for all of our confidence intervals. And all we need to know for each additional situation is what's the point estimate, what's the critical value, what's the standard error. All right, well, now we're kind of done with our handwork. That seemed really quick, but yeah, I guess that's kind of it. So let's go on and do some built-in functions for our simple linear regression case. So remember, we have our simple linear regression model that's still floating around here. So first of all, how I find the statistics for my simple linear regression model, all of the analysis stuff, is by using the summary of SLR mod. And this table right here is what a typical regression output table is going to look like when you run a regression using software. It's going to give you the intercept and then the different independent variables. Then it'll give you your parameter estimates. This is my B0 and B1. Then it gives me my standard errors of these, S sub B0 and S sub B1. Hopefully, if we calculated these correctly, S sub B0, S sub B1, note how quickly it is to find standard errors in the built-in stuff. It gives me my test statistics and it gives me my p-values. I guess I can check my latest p-value. So can't check the earlier one because I overwrote the TS variable with my new calculation. Anyway, so can check my p-value, and yeah, that all matches, that all works out. Everything looks good. So there's a ton of information included in this summary of the ANOVA model. So remember how we built the ANOVA model up top. The ANOVA model is just LM, put my dependent variable, squiggle, independent variable. And then using the summary command for that gives me a ton of information. Not only that, but notice what else this gives me. I get the residual standard error. This is the S value. I get the degrees of freedom. I get R squared. So if I calculate R squared, oh, I deleted R, unfortunately. So that was from a previous video, I guess. But let me just quickly find this core marketing and profit. So this is a correlation. Square it, 0.4248, 0.4249 with rounding. Yes, I get my R squared. We'll talk about adjusted R squared later. Not yet. And I get my overall ANOVA. I get the overall ANOVA p-value. So I get a ton of information in this summary of the regression. It's very, very, very concise, but this is everything I need to make my decision. So I'd look here, say yes, no statistically significant marketing effect, and recall Overall, that means that there's not evidence that there's a slope greater than 0 or less than 0, different. But that also means that there's not evidence that there's any kind of relationship, linear relationship between marketing and profit based on this data. Now, we talked about how to do the confidence interval for beta 0 and beta 1. To do a confidence interval using built-in functions, you do the confint command, give it slr mod, and here we have our confidence interval. So we said negative 0.206 to positive 1.43. That was our confidence interval for the slope, and then our confidence interval for the intercept. Can we run that? Did we overwrite anything? I don't think so. Negative 9.4, yes. 3.875, yes. All right, perfect. So again, we can kind of replace all of this handwork if we want to, that we spent all of this video doing, with some pretty slick built-in commands to very quickly get what are my slope and intercept, slope, what are the standard error of the slope, or standard error of the intercept, excuse me, standard error of the slope, test statistic, p-values, what's my r-squared, what's my s value if I need to use that, as well as the confidence intervals for the intercept and slope, all pretty easily using the built-in functions. All right, ladies and gents, well, this has been a video where we talked about how we can do the inference testing for our simple linear regression in R. We talked about building up the hypothesis tests and all the things that we needed for like the standard error and the mean squared error, how to find all those by hand or by calculating them in R, doing the actual calculations and computations in R. Talked about how we can use those to do hypothesis tests for both the intercept and the slope, and then how we can use them to build confidence intervals for both the intercept and slope. Finally, we closed out with the built-in functions, which make all that just so easy when we have raw data. Big fan of built-in functions, and again, they're not cheating, they're the whole point. My goal is that you focus more and more on the interpretations. How can we actually use this as we progress through the course? Less and less than the computation. There's still a few problems that you might have to do the computations because you may or may not have the raw data, or they might ask for some specific statistics from the computation process. But by and large, hopefully you get to start thinking more and more about, okay, what does the p-value mean again? What does significance mean again? How can I use the result? How does this impact business practice? What should I not use this for? In what cases would this be an inappropriate conclusion, etc.? So I hope you start thinking through a lot of that as the focus decreases on manual computation. But yeah, those built-in commands, man, they save a lot of time. They're really, really useful. And again, I use them all the time. They're how I do analyses. I don't do it all by hand unless there's something bizarre going on. I use the built-in commands and interpret from there. And that's kind of the starting place for me. Get data in, use the built-in command, and then yeah, interpret it and move on. Start to talk about, okay, where can we use this? How can we use this? What does this mean? What does this say? What does this not say? Etc. But this table, this is my starting place when I do analysis after the data are entered. So anyway, thanks for sticking with me through this video. I appreciate it, and I will look forward to catching you in the next one.